All right, let's talk about a force that's all around us. You can't see it, but you can definitely feel it. I mean, it literally powers our entire world. It holds matter together, and it's even responsible for that little zap of static you get on a dry day. Today, we are diving deep into the incredible, invisible world of electric charge.
You know exactly what I'm talking about, right? You walk across a carpeted room, you reach for a metal doorknob, and zap! You get that tiny but surprising shock. It might seem totally random, but it's not just some weird fluke. That little spark is actually your own personal encounter with one of the most fundamental forces in the entire universe. Or hey, maybe you've done this little experiment before. You run a comb through your hair, and then you watch as it magically picks up little scraps of paper. It seems like a magic trick, right? But it's not. Both that spark and this little trick are caused by the exact same thing, this invisible force we call electric charge.
So how do we get from a simple spark at a doorknob to, understanding the cosmos? Well, here's how we're going to break it down. We'll start with that shocking feeling, then we'll meet the tiny particles that carry charge. After that, we'll learn the super simple rules of attraction, figure out why some materials shock us and others don't, and finally, get into the really cool stuff, how to charge something without even touching it. So let's dive in.
First up, that shocking feeling. So what is really going on when you get that static shock? Where does this mysterious thing called charge actually come from?
Well, the answer isn't on the surface of your skin, and it's not really in the doorknob itself. To truly get it, we need to zoom in, way, way in, down to the very building blocks that make up everything.
Which brings us to Section 2, the particles of charge. Welcome to the world of the atom. Everything you see, everything you touch, it's all made of these tiny things. And the secret to electric charge? It's locked right inside them.
So what is an atom? It's the basic unit of all matter. It's got this super dense little core called the nucleus, and that's surrounded by a cloud of even tinier things called electrons. And the scale here is it's wild. If you imagine an atom being the size of a giant stadium, the nucleus, where almost all the mass is, would be the size of a single marble sitting right in the center.
Now, inside that atom, we've got three key players. In that tiny nucleus, you have protons, which have a positive charge, and neutrons, which, as their name suggests, are neutral. They have no charge at all. Then, zipping around that nucleus, you have the electrons, which have a negative charge. But look at the mass difference. Protons and neutrons are huge by comparison, almost 2,000 times more massive than those little lightweight electrons.
Okay, so here's where it all clicks into place. It's all about balance. In a normal neutral atom, the number of positive protons is perfectly balanced out by the number of negative electrons. The net charge is zero. But if an atom loses one of those flighty little electrons, the balance is thrown off. It now has more positive charge than negative, and we call that a positive ion. And you can probably guess the opposite. If it grabs an extra electron from somewhere, it becomes a negative ion.
And this brings us to a fundamental, unbreakable law of the universe, the conservation of charge. You can't just create charge out of thin air, and you can't destroy it. All you can do is move it around. So when you rub a plastic rod with fur, you're not making charge, you're just a transporter. You're simply moving electrons from the fur onto the rod. The fur becomes positive, the rod becomes negative, but the total amount of charge in the universe stays exactly the same.
Okay, Section 3, the rules of attraction. So we know charge is just an imbalance of protons and electrons. But how do these charged things interact? Well, it all boils down to two incredibly simple rules.
Rule number 1 is easy. Like charges repel. That means two positive charges will push each other away. And two negative charges? Same deal. They want nothing to do with each other. Here's a perfect example of that. You take two plastic rods, you rub them both with fur so they both get a negative charge. Then you bring them near each other, and you can literally feel them pushing each other apart. That's repulsion, right there in your hands.
And rule number 2 is, you guessed it, the complete opposite. This is where all the action is. Opposite charges attract. A positive and a negative charge will always pull towards each other.
And we can see that happening right here. We've got our negatively charged plastic rod again, but this time we bring it near a glass rod that's been rubbed with silk, which makes the glass rod positive. Instead of pushing away, they pull towards each other. They attract. And that's really it. That's the core of electrostatics. Likes repel, opposites attract. Section 4. Conductors versus insulators. So we know the rules of charge, but this leads to a pretty good question. Why does a metal doorknob give you that shock, but a wooden one probably won't. Well, the answer has everything to do with how easily charges can move around.
So materials basically fall into two camps. First, you have conductors, like copper and most metals. In these materials, some of the electrons are really loosely bound to their atoms. They're like free agents, able to roam around wherever they want, which means charge can flow through them super easily. Then you have insulators, like rubber or glass. Here, the electrons are held on a very tight leash. They can't move. So charge can build up on an insulator, but it can't travel through it.
And this brings us full circle, right back to that doorknob. When you scuff your feet on the carpet, you build up an excess of charge. The metal doorknob is a conductor. It provides a perfect pathway for that extra charge on your body to leap from your finger to the knob in a sudden, tiny lightning bolt, and that's the spark. But a wooden doorknob is an insulator. The charge gets to your finger, sees the wood, and has nowhere to go, so no sudden discharge and no shock.
All right, section 5. This is my favorite part where things get really clever. It turns out you don't actually have to touch things together to move charge around. You can actually manipulate objects from a distance using two tricks called induction and polarization.
So first, let's look at charging by induction. It's like mind control for electrons. You take a charged rod and just bring it near a neutral metal sphere. The like charges in the sphere get scared away and run to the far side. Then you give those scaredy-cat charges an escape route, like a wire connected to the ground. Poof, they're gone. Then you remove the escape route, trapping the remaining opposite charges. You pull the rod away and voila! The whole sphere now has a net charge, and you never even touched it.
But what about an insulator? The charges can't run away, remember? They're stuck. Well, you can still influence them. Imagine every atom inside is like a tiny little compass. The compass can't leave its spot, but if you bring a magnet nearby, all the needles will turn to face it. That's polarization. The charges don't leave, they just realign.
And that is the secret behind our comb trick. The pieces of paper are neutral overall, but when you bring the charged comb close, the charges inside the paper polarize. One side of the paper becomes a little bit positive, and the other a little bit negative. And because the attractive force on the near side is just a tiny bit stronger than the repulsive force on the far side, attraction wins, and the comb lifts the paper.
So, you see, these simple principles we've been talking about, likes repel, opposites attract, and the whole conductor versus insulator thing, they're not just abstract ideas in a textbook. They explain everything from that little spark at your fingertip to the incredibly complex workings of technology we use every single day, like a laser printer using static to place toner perfectly on a page.
But here is the biggest, most mind-blowing reveal of all. This invisible force, it does so much more than cause static cling. It's the force that binds atoms together to make molecules. It's the force that holds those molecules together to create you, me, the chair you're sitting in, everything. In fact, the only reason you aren't falling through the floor right now is because the negative electrons in the floor are repelling the negative electrons in your feet. It's electric charge, this invisible force, literally holding our entire world together.